So in some of the last sessions, we've talked about the properties of our sun, some of its structural properties, solar activity, the fusion reaction that's going on inside of the sun. But when we look at the night sky, we see many, many stars. There's huge numbers of stars. And basing all of our information about stars off of a sample size of one is probably not going to be a great idea. It's not going to be very reliable for us. Unfortunately, all other stars are so far away that we can't really send any spacecraft or probes to other stars using current technology. So what are some of the ways that we can actually try to measure some of the properties of these stars, even though they're so distant? Basically, all we're going to have to go off is the light that comes to us from those distant stars. But we want to measure a number of different properties. We might want to measure things like how far away is the star? What is the luminosity of the star? Basically, how much light energy is it giving off overall? The temperature of the star, the size of the star in terms of its radius, what's the mass of the star? All of these different properties that we'd like to know about stars, but we're kind of stuck here on the Earth. Again, these other stars are so far away that with current technology, it's infeasible to actually send a probe to these other stars. So we're going to go through some of these properties and say, well, how can we actually measure these from the Earth? And we're going to start with talking about how do we measure stellar distances. There's actually a whole set of techniques that we can use to measure distances, and each technique allows us to measure the distances to further and further objects. We're going to talk about this at a number of different points throughout the course. For now, we're going to talk about measuring distances to relatively nearby stars. And then later on, we'll talk about other methods that allow us to measure more and more distant objects in a method that's called the cosmic distance ladder. But at least for now, we're going to focus on what's called the parallax method. So if we're trying to measure distances, we're using this parallax method. And this method is very, very similar to how our eyes understand depth perception. How do we see depth perception? So think for a minute about how do your eyes actually have depth perception? How can you tell how close an object is or how far away an object is, especially if you don't necessarily know how large the object is? Like, yeah, if I hold my calculator up close to me, I know how large the calculator approximately is. So my brain goes through and tries to determine how close it is. But how do our eyes generally determine the distance to an object? Well, one key aspect is that we have two eyes. And our two eyes, when you look at something through your left eye or through your right eye, it will see a slightly different image. So let's say I'm looking at this star and I have this colored background and I'm looking through my left and my right eye. Well, my left eye, based on what it sees, it's going to see this object in front of this red panel. My right eye will see the object in front of the blue panel. You can try this yourself. So take your finger and hold your finger up in front of you, maybe about a foot away from your face. And then close one eye and look at where your finger is compared to some background objects on, say, the other side of the room. So look at the far side of the room and say, well, my finger seems to be in front of one part of the back of the room. And then switch eyes and go back and forth between looking at your finger using your two eyes. And you'll notice that when you switch eyes, your finger seems to jump compared to the background objects that you're looking at. Again, from one eye, it might look like it's in front of one part of the distant object. Through my other eye, it's going to look like it's in front of a different part of that distant object. So again, try that with your finger up close. And now move your finger further away from you and repeat the experiment. And look at how much your finger appears to shift compared to those background objects. So try it now, and then we'll talk about the results. Well, basically, the further away your arm is, the smaller the shift it seems to make compared to that background. So I'm actually going to try to simulate this with my camera. Okay, so what I've done is set up a couple of objects on this table over here, and I've got my camera here, and you can see my view from the camera. Okay, so I want to look at, let me just set this up here. I want to look at how the camera's view of these two objects, the nearby object and the distant object, compared to the door in the background when I move my camera from side to side. So if I start moving the camera to the side, notice that both objects appear to move compared to that background. Kind of looking up a little bit too much. Both objects appear to move compared to the background, but you'll notice the object that's closer seems to move significantly more than the background object does as I move that camera from side to side. Okay. Again, your eyes do this automatically. When you're looking at an object, your two eyes are getting slightly different images, and based on how much the object in the foreground is shifted on the background, your brain goes through all the work in trying to process that information to get a 3D representation of where objects are. Now, you might think, well, how am I going to get the best depth perception possible? Because if I only move this a tiny, tiny bit, if I only move the camera back and forth a tiny, tiny bit, there's not much of a shift. So think about this one. How would I improve my depth perception if my eyes were closer together or if my eyes were further apart? Again, when I'm making these questions, pause the video and have a think about them. Well, if my eyes were close together, that would be like just barely moving the camera from side to side. I almost don't see any shift at all. However, if my eyes were further apart, well, that corresponds to a greater shift in both of those objects. That's going to be more, it's going to be easier to detect. So if I want to measure the distances to different stars, I effectively want my two eyes to be as far apart as possible. For the purpose of this discussion, let's assume that we are stuck on the Earth. We can't use spacecraft or anything like that. How could I make two observations that are as far apart as possible? If I'm trying to look at a star and measure its distance, I want to make two observations from locations that are as far apart as possible in order to get my eyes, my quote-unquote eyes, as far apart as possible to get that depth perception, to get that parallax effect, and to measure the distances to these stars. So pause the video and think, how could I take those two observations as far apart as possible? And here's a hint. Those observations do not need to be made at the same time. So think about that one for a second. Okay. So some of you may have said, well, maybe put them on either sides of the Earth. That actually works for measuring the distances to objects like objects in the solar system. So some of the nearby planets, things like Venus, that's part of how we measure the size of our solar system. But there's actually an improvement that we could make because our Earth is not stationary. If we draw the solar system, we've got the sun, and let's say we've got the Earth over here, and the Earth is going through some orbit. It takes 1 year to make a full pass around the sun. Well, let's say there's some distant star that we're trying to measure compared to some background stars. This is definitely not to scale. If I make the measurement, make the observation of this star at 2 times of year, at 2 points in the year, when the Earth is at on two different sides of the sun, well, at 1 time a year, I'm going to see that star in front of some background objects. 6 months later, I'm going to see the star in front of some other background objects. So for this parallax method to work, because stars are so distant, we actually need to use the entire size of Earth's orbit as our kind of observing platform. So again, the furthest we can kind of set our eyes apart are at opposite ends of the Earth's orbit. So from over a 6-month period, you'll actually observe that the locations of relatively nearby stars will shift on the sky compared to background stars. And this allows us to measure something called the parallax angle. So the parallax angle, let me write this one down. The parallax angle basically is a measure of how much, by what angle has the apparent position of that star seemed to shift on the sky over the course of the Earth's orbit. So the parallax angle is the apparent shift, the apparent angular shift in position of a star in the sky. We're not going to worry about the exact geometry of this. Technically, this angle labeled here would be twice the parallax angle, so this is twice the shift. But basically, the larger the parallax angle, the closer the star is to Earth. Just like when you hold your finger up in front of you, close to your face, when you switch eyes, there's a bigger apparent shift compared to the background than if you hold your finger further away. So the larger the parallax angle, the closer the star is to our solar system. So larger parallax angle means closer to our solar system. Again, when we're talking about things like angular distance or angular size, I mentioned this briefly when we talked about a telescope's angular resolution, the smallest angular feature it can see on the sky. Angular distances are sometimes measured in degrees. For astronomy, sometimes measured in something called arc seconds. And again, this angular distance is how separated two objects appear to be on the sky. And just for some comparisons, if you hold up your little finger at arm's length, the width of your little finger is approximately 1 degree on the sky. However, stars outside of our solar system, other than the sun, all other stars are so far away that these parallax angles are very small, very difficult to measure. So instead of measuring these angles in degrees, we talk about arc seconds. So let me define an arc second. So these parallax angles are measured in arc seconds. In arc seconds. And basically 1 degree on the sky is equal to 3,600 arc seconds. So if you think the width of your pinky finger is 1 degree, an arc second is 3,600 times smaller an angle than that. As another way of comparing it, 1 arc second would be the apparent size of a quarter if you were viewing it from 3 miles away. These parallax angles that we're measuring are very small. And even with that very small angle, all stars have a parallax angle of less than 1 arc second. We're going to talk about this equation in just a minute. All parallax angles are less than 1 arc second for all stars that we've measured. Which means this is incredibly hard to detect, and this wasn't actually successfully measured until the early to mid 1800s. In fact, this difficulty in measuring the parallax angle was actually an argument against the sun-centered Copernican model of the solar system, because people were saying, well, if the Earth is orbiting the sun and on this moving platform, we should be seeing shifts in the positions of all these stars over the course of a year, unless stars are just so ridiculously far away that these parallax angles are too small to currently measure. Well, it turns out that those parallax angles, those stars were all just too far away for those angles to be measured until, again, the first ones in the 1800s, and again, more and more as technology has improved. So let's talk about how we can actually use this parallax angle to measure the distance. Here's the equation that we're going to be using. The distance to a star is equal to 1 over that parallax angle. Now, there are a couple of important parts of this. This distance, when we're using this equation, this distance is in a unit called a parsec. And this parallax angle is measured in arc seconds. So whenever you're using this equation, the distance must be in parsecs, and the parallax angles must be in arc seconds. I know these terms are confusing. Parsec is a unit of distance. Arc seconds is a unit of angle. Okay. And this parsec value, 1 parsec, or PC for short, is equal to 3.26 light years. The way that this definition kind of comes about is basically, in order to calibrate this equation, we need to know the size of the Earth's orbit. So the size of the Earth's orbit is involved in actually figuring out this definition of parsecs. But again, by the 1800s, we actually had some decent measurements of how large our solar system is and the size of Earth's orbit. Now, this method works generally out to distances of around a little over 1,000 light years. And actually, since the Gaia mission was launched and started taking data, I think it was launched in 2013 and has been taking data since then. The Gaia mission, which is a satellite to try to measure these very, very small parallax angles, and has been actually immensely successful in measuring these parallax angles, the Gaia mission can make measurements out to, I think, a couple tens of thousands of light years in under ideal circumstances. So we've increased this distance to about, a few tens of thousands of light years using the data from this Gaia mission. Again, if the parallax angle is larger, if I do 1 divided by a larger number, that distance is going to be smaller. The larger the parallax angle, the closer this thing is to our solar system, the smaller the distance. So let's try an example of this. Suppose I look at this star, and over the course of this 6-month period, we see the shift in position of that star corresponds to a parallax angle of 0.13 arc seconds. And I want to know, what is the distance to this star? Well, in our calculation, we'll say the distance is 1 over the parallax angle. Well, we said our parallax angle is 0.13 arc seconds, so it's already in arc seconds, so we don't have to do any conversions or anything like that. And if I plug that into my calculator, 1 divided by 0.13, we get an answer of about 7.7. 7.7, and this would be in units of parsecs. Whenever we use this equation, we have arc seconds for the parallax angle, and the distance we get out of that is in parsecs. If I wanted to convert that from parsecs to a distance in light years, well, we can use this unit conversion and say, well, if 1 parsec is 3.26 light years, we can do the unit conversion like this: 7.7 parsecs. And for every 1 parsec, that's 3.26 light years. Notice that in this equation, the parsecs will cancel out. And in this particular case, we're left with around, let me see, it's around 25 light years. Let me double check that with my own calculation. Yeah, 25.1 light years. 25.1 light years of distance. So again, if I know the parallax angle, I can use this to figure out what is the distance to this star. The larger the parallax angle, the closer the star is to our solar system. So again, bigger parallax angles means the star is close by. Smaller parallax angles means the star is further away. And this equation specifically allows us to figure out exactly how far it is. If I know that parallax angle in arc seconds, I can calculate the distance. So let's look at some examples. Suppose I had a couple of stars and I want to know which one is closest to us. So we have a few stars and their parallax angles in arc seconds. Well, pause this one and try it for yourself, and then I'll talk about the answer in just a moment. Okay. Well, we said that the larger the parallax angle, the closer it is to us. So we're looking for the star that has the largest parallax angle. Barnard's star is largest parallax angle, so that means it's also the closest to us. What if I wanted to put the following stars in order from closest to us to furthest away? So again, pause the video and try this one for yourself. Okay, so we want to go from nearest to us to furthest away. Well, the closer it is to us, the larger the parallax angle. So Sirius looks like it's the largest parallax angle, so that's closest to us. Followed by Vega would be next closest, Capella after that, and Aldebaran to kind of end out this list. So nearest is Sirius, then Vega, Capella, and Aldebaran. Let's do a couple more calculation examples. So I'm going to erase a little bit of this stuff and make some room. Let's try this one. Sirius has a parallax angle of 0.379 arc seconds. Calculate the distance to Sirius in parsecs and then in light years. Once again, try pausing the video and try this for yourself before I go over the solution. Okay, so for this one, we're saying Sirius has a parallax angle of 0.379 arc seconds. So that's going to be plugged in for our parallax angle, so 0.379. If I plug in 1 over 0.379, that gives me 2.64 parsecs. So that's just the distance of this star in parsecs. If I want to convert that distance from parsecs to light years, well, 1 parsec, I want the parsecs to cancel out, so I'm going to put 1 parsec in the denominator, is equal to 3.26 light years. The parsecs cancel out, and if I multiply 2.64 times 3.26, I get around 8.61 light years. Note that if I wanted to convert from light years back to parsecs, instead of multiplying by 3.26, I would divide by 3.26. And it looks like these numbers are matching up for that. Let's try one more. Altair has a parallax angle of 0.19 arc seconds. So the little double tick mark on there just does denote arc seconds. I want to again calculate the distance to Altair in parsecs and in light years. Oh, same kind of idea. If I have the parallax angle, in this case, it's 0.19 arc seconds. And I plug that in, 1 divided by 0.19. That gives me 5.26 parsecs. Notice that this parallax angle is a little bit smaller than the one that we had in the last example for Sirius. The parallax angle is a little bit smaller, so the distance is a little bit larger. Again, if I want to convert this to from parsecs to light years, 5.26 parsecs. 1 parsec is 3.26 light years. When I plug in the number 5.26 times 3.26, I got 17.1. 17.1 light years. Now, again, the best measurements of this parallax effect that we have are from the Gaia mission. The instrumentation on that Gaia satellite, it's a satellite that's orbiting a couple million miles away from Earth at a point called the L2 Lagrange point. So it kind of, if here's the sun and here's the Earth, that L2 point is a little bit further away, but it stays kind of aligned with the Earth as it orbits around the sun. And its instrumentation is so sensitive that in ideal circumstances, it can measure these parallax angles down to around 10 millionths of an arc second. Again, it is just fantastic, kind of cutting edge technology. And they've actually made measurements of, I think at this point, over 1.4 billion individual stars, measuring their parallax angles, their proper motion, a whole bunch of things about some of their color properties, like what are the colors of these stars. Just a huge amount of data that scientists now can work with. Okay, so in summary for that one, if we're trying to measure distance, we're going to use this parallax effect. And if I know the parallax angle, I can actually calculate directly what is that distance. So now we want to talk about measuring luminosity. Let's change up a little bit, and we're going to measure luminosity. So again, luminosity, as we talked about when we talked about the property of the sun, luminosity is the total power output from the star in watts. Total power output in watts. That is not something that we're going to be able to directly measure. If I wanted to directly measure the luminosity of a star, I'd have to basically surround it in solar panels, collect all of the light energy that's coming off that star, and measure it that way. Probably not going to happen. We're not going to be building a Dyson sphere anytime soon. And again, these stars are very far away. One thing that we are going to be able to measure is the apparent brightness. So that luminosity, we're going to call that L. We also have apparent brightness. Which I'm going to denote with a lowercase b. This is basically a measure of what is the amount of light energy arriving at the detector, arriving at your telescope in watts per square meter. How much power is reaching your telescope per square meter of the telescope? And this very closely correlates with how bright does that object appear to be to our eyes, to a telescope when you look at it. So that's the apparent brightness. The amount of light arriving at telescope per square meter. So that's actually measured in watts per square meter. So again, apparent brightness, we can directly measure that. We can say, I'm aiming a telescope at this star. I know how much light is being collected. I know the area of the, collecting surface of the telescope, and we can actually measure this apparent brightness. The luminosity of this star, well, we can't really directly measure that, but we're going to see how we can infer what the luminosity must be if we have the apparent brightness and also know the distance. So let's look at how we would do this. We've got three quantities: apparent brightness, luminosity, and the distance to the star. So again, the apparent brightness is what you see. How bright does this star appear to be to our eyes? And this is a quantity that we're going to measure in watts per square meter. The luminosity is just how much light energy overall is this star outputting. So that's the intrinsic power output in watts. And we've also got the distance from our observing location, probably in our solar system on the Earth, to that distant star. We can relate those quantities using this equation. So let me write this one down, because this is the next equation that we're going to be playing around with. The apparent brightness equals the luminosity divided by 4 pi times the distance to that object squared. Let's play around with this just a little bit and see how these quantities relate to each other. So let's say I'm looking at a light bulb, and it has a certain power output. Let's say it's a 100-watt light bulb, and it's a certain distance away. To my eyes, it has a certain apparent brightness. If I switched out the 100-watt light bulb with a 200-watt light bulb, what would I probably say about the apparent brightness of that object? Yeah, if all we do is switch out the 100-watt light bulb for a 200-watt light bulb, what's happening is we're increasing the luminosity. Luminosity is in the numerator of the equation. So if I increase that luminosity, apparent brightness is going to increase as well. On the other hand, let's say I took that original 100-watt light bulb, and instead of having the 100-watt light bulb right here, I move that 100-watt light bulb much, much further away. So I'm increasing the distance to that object. Well, if I increase the distance, then in this equation, distance is in the denominator of the equation. And if I make the denominator of an equation larger, the denominator of a fraction larger, that will have the effect of decreasing the value of that fraction. So if I take that light source and all I do is increase the distance, that means it will be less bright. The apparent brightness will be less to our eyes. So one way of thinking of this is think of the light energy that's being given off by that source. Let's say I have a light bulb and it's giving off energy in all different directions. Well, as that light energy moves away from the source, you can think of that light energy as being deposited on the surface of a sphere. And the further that light has traveled, the larger the surface area of that sphere. In fact, the amount of area, if I take part of that light, the amount of area that light energy is spread out over depends on the distance squared. If I double the distance, well, that energy is being spread over 4 times the area, which means that if I double the distance, to my eye, it will appear a quarter the brightness. That's basically where this squared term comes in for talking about this distance. In fact, those of you who have taken some geometry courses or remember something from a, long ago geometry course, you might recognize this 4 pi, usually you'd see it as 4 pi r squared as the surface area of a sphere. So again, that's involved in actually deriving this equation. I'm not expecting any students to derive this equation. This will be something that's given to you on the test. But again, basically, as I move further from the source, the apparent brightness, aka the intensity, is going to decrease. We're going to see this equation rearranged in different forms. So it's good to be comfortable with being able to rearrange this into different forms. For example, I could rearrange this into luminosity is the brightness times 4 times pi times the distance squared. Basically multiplying both sides by 4 pi distance squared. Or I could rearrange this and solve for distance. Distance is the square root of luminosity over 4 pi times the brightness. Because in most cases, I don't know if I'd say most cases, in many cases, when we're looking at a star, if I know the apparent brightness, that's something I can directly measure. Again, it's how much light energy is hitting our telescope. And if I know the distance, say I've already done this parallax measurement and I know the distance of that star, if I measure that apparent brightness and I know that distance, I can use that to figure out what the luminosity of the star has to be. Remember, we can't measure this luminosity directly, so we have to infer what the luminosity of the star is based on the apparent brightness and the distance to the star. Another thing that we'll see later on is there are certain kinds of stars where we might know their luminosity. After having studied a population of stars, we might identify, oh, these types of stars with these properties, they have this luminosity. So if I know the luminosity and I measure the apparent brightness, well, we can actually use this as a way to measure even greater cosmic distances. This is actually one of the next rungs on that cosmic distance ladder, when objects are too far away for us to be able to measure their parallax. Well, if we find certain classes or types of stars that have a known luminosity, that have a reliable luminosity, we can use those and say, if I know the luminosity and I measure the apparent brightness, we can figure out the distance to those stars. So what kind of questions are we going to see for this? Most of the questions that I'm going to ask on this brightness, luminosity, and distance equation are going to be those kind of comparison style questions. So we saw some of these when talking about Newton's law of gravitation. We're going to see more of these comparison questions here. So let's look at an example. Suppose star B is 0.25 times the apparent brightness and 5 times the distance of star A. I want to know, how do the star's luminosities compare? Make sure you're being careful when you're talking about brightness. I probably should have been a little bit more careful in this particular question and said the apparent brightness, because brightness, when you just say brightness, it can be unclear whether you're talking about luminosity, the power output of the star, or how bright does it appear to be based on our distance to the star. But let's say this is apparent brightness. So star B has 0.25 times the brightness, the apparent brightness, and 5 times the distance of star A. How do the star's luminosities compare? Again, this is a comparison style question, so let's look at the general format. The general format for a comparison style question is, first, identify what kind of quantity you're being asked to compare. In this case, we're being asked to compare what's happening to the luminosity when I change the apparent brightness and when I change the distance. So let's write down this equation when we're solving for the luminosity. In this question, I do not say what the original brightness, apparent brightness of either star is. I don't tell you what the distance to either star is. So in these kinds of cases, when I don't give you any numbers and it's a comparison style question, make something up. Let's say star A is our original case. I don't know the brightness. I don't know the distance. Let's call them both 1. Let's say the apparent brightness of star A is 1, and the distance to star A is also 1. So if I multiply this out, I'm just going to get 4 pi. I'm not even going to bother multiplying out what 4 pi is. Okay, basically 1 times 4 pi times 1 squared is just 4 pi. Okay, so that's our original case. And then we want to look at our new case. What is star B doing? So for star B, well, it's 0.25 times the apparent brightness. For star A, I said 1 was the original apparent brightness, so I want 0.25 times that. Again, this is one reason why it's nice just using ones to begin with, because when we're saying it's only 0.25 times, if we're starting with 1, we can just use 0.25. Times 4 pi times the distance squared. Well, we're saying star B is 5 times further away than star A. We said star A's distance was 1, so we're now changing that to 5 for star B. I'm going to leave the 4 pi the same and multiply out 0.25 times 5 squared. So all the new numerical terms that we've introduced, let's multiply those together. So 0.25 times 5 squared, I get 6.25. So again, all I did here was say we have our original case where we used ones for all the quantities that we were not given. In my new case, well, the apparent brightness changed, the distance changed, and I'm seeing what sort of difference we have in the luminosity of B compared to the luminosity of A. And the last step in any of these comparison questions is to say, what is our new value divided by our original value? So in this case, our new value is 4 pi times 6.25. Our original value was just 4 pi. Notice that the 4 pi cancels out, so that's why I didn't bother multiplying that out to begin with. And we're left with a result of 6.25. What this means, again, there's a more kind of mathematically detailed way of doing this. I like generally just subbing in numbers for the first made-up case and then seeing how things change in the new case. This one I definitely should change. Star B is 6.25 times as luminous as star A. Because again, the thing that we were comparing was the luminosity, not the intrinsic brightness of the star. I think I'll correct this and change this to luminosity before I actually post these notes. So it should be star B is 6.25 times as luminous as star A. Okay, let's try a couple more examples, because the examples that we're going to look at for these kind of comparison style questions, you'll either be comparing the luminosity, comparing the distance, comparing the apparent brightness, and the setup is going to be the same. Identify which quantity you're trying to compare and use that rearrangement of the equation. Make up numbers for your original case. Look at what numbers change for your new case, and then do your new case divided by your original case, and that will give you how that quantity compares, how the new quantity compares to the original quantity. Let's do a couple more examples. Suppose 2 stars have the same luminosity, but one is twice as far away as the other. Which statement is true about their apparent brightnesses? So pause the video and see if you can work through this question. Let's get a clean slate here. Okay, so in this case, we're being asked to compare the apparent brightness. So this is the form of the equation that we will be using. And once again, I've not been given any numbers, but let's try this out. Let's say this is the brightness of the close one. Let's make that our original. Let's use ones for all of our original points. So luminosity is 1, 4 pi times the distance is 1. That's going to be squared. So we get 1 over 4 pi. And I'm just going to leave that. You're going to notice that the 4 pi is going to cancel out anyway. In fact, since we know the 4 pi is going to cancel out, for these comparison style questions, it's sometimes easier to just drop the 4 pi. Just get rid of it. We'll do an example like that. We'll do another example like that in a couple minutes. But in the far case, we're saying one star is twice as far away, but they have the same luminosity. So the luminosity, we don't change. But that distance, we're going to double that. So this is going to give me, I still get the 1 over 4 pi, but 1 over 2 squared, that's an extra 1 over 4 term. 2 squared is 4, so we have 1 over 4 multiplied in here. So it looks like when we do the last comparison, when we do that comparison, so the far one compared to the close one, the far one is 1 over 4 pi times 1 over 4. The close one is just the 1 over 4 pi. Again, the 1 over 4 pi cancels out. So this is why it's sometimes easiest to just drop the 4 pi right off the beginning. Yeah, we'll do another example of this, showing that explicitly. So this just ends up giving us 1 over 4. The far object is 1/4 the apparent brightness of the close object. So we would say the further star is 4 times dimmer than that close star. So that would be option C for this one. Before we do that one, let's try, let's say I change the numbers, but instead of this one, we said 1 is 3 times. One is 3 times as far away from the other. And let's see what happens when we do that, dropping the 4 pi term. So I can erase this one. I recommend you try this one again yourself before we go through the numbers. In the close case, we're saying, again, I'm just making up numbers. I'm going to say the luminosity is 1. I'm going to say 4 pi is equal to 1. I'm basically going to effectively drop that term. And the distance is still 1. So in this case, I'm just setting even 4 pi. I'm just going to make that 1 for the purposes of this question. For the far one, same luminosity, but it's now 3 times further away. Well, remember, we have to square that 3, so we're going to get 1 over 9. And if I do b far over b close, that's going to be 1 over 9. Basically 1 over 9 over 1. So the far star would be 9 times dimmer than the nearby star in that case. Okay, let's look at another example. Suppose 2 stars have the same apparent brightness on the night sky, but one is 3 times further away than the other one. And I want to know how their luminosities compare. So in this case, well, again, pause the video and try giving this one a try. Okay, so in this case, we're being asked to compare the luminosity. We're going to want this luminosity version. Well, let's say we've got the same apparent brightness. Let's say we've got L close is, well, we have to make up numbers in our original case. So let's say the apparent brightness is 1. Let's say 4 pi is equal to 1. And let's say the distance is 1. We still have to square that distance. In this case, we get 1 all around. For the far object, well, it's got the same brightness. We're still saying 4 pi is equal to 1, but now we want this star to be 3 times further away. That's going to give us 9. And again, you can go through that L far divided by L close. So the new case divided by the original case. Notice that when you set everything to 1, this last step becomes a little bit unnecessary since we can see, oh, it's 9 times larger. That further star is 9 times as luminous as the nearby star. Let's do a couple more examples. I don't want to belabor the point too much, but I think some students might want to see more examples, so hopefully this is helpful. Let's try this one. Suppose star A is 4 times more luminous as star B. Star A is also twice as far from Earth as star B. And we want to know how the brightness compares. So let's give this one a try. We want to know how the brightness compares. So we're using this form of the equation, L over 4 pi d squared. And let's start with star A. This is going to be our reference star. The luminosity is 1. 4 pi is equal to 1. Distance is going to be 1. So again, I'm doing that thing where I'm just saying the 4 pi, it's going to cancel out anyway. So let's just call it 1, make our lives a little easier. In the new case for star B, we said I think I got these backwards. So I'm going to call this one B and this one A, because I said star A is 4 times more luminous than star B. So let's make star B our reference case. So star A is 4 times more luminous, and the distance, star A is twice as far away from Earth. Well, notice when we run through the numbers on here, we're going to get 4 divided by 2 squared. 2 squared is equal to 4, so we get 4 over 4, which is just 1. So in this case, when we compare star A to star B, well, 1 over 1 is just 1. So these two stars will appear equally bright on the night sky. So again, these kind of comparison style questions, we're going to keep on seeing questions of this variety at a bunch of different points throughout the course. Let me do one more involving distance. I haven't included this on the slides, but this will be a bonus for people who are still sticking through the video. Let's talk about the distance. Let's say star B appears twice as bright. But we also know it's 5 times more luminous. So 5 times more luminous than star A. So somehow we already know the luminosities of these stars. This is not the standard way that this would be done, but again, good to just get a complete set on here. So star B appears twice as bright, but it's actually 5 times more luminous than star A. And I don't know, how are the distances to these stars going to compare? Well, in this case, we're comparing the distance. So again, we have this rearranged version of the brightness equation. Basically, the way you get this is, let's multiply both sides by d squared. So the d squared would come onto this side. And then we'll divide both sides by the brightness, and then take a square root of both sides. That's essentially how you do that rearrangement to get this formula. So let's see how this plays out. So let's use star A as our reference case. Again, we're just plugging in fake numbers. So let's say if it's a reference case, let's just use ones for everything, one for the luminosity, one for 4 pi, one for the brightness. And the square root of 1 over 1 times 1 is just 1. In the new case, well, we're saying star B is 5 times more luminous, yet even though it's 5 times more luminous, it only appears twice as bright. So when I go through this, 5 divided by 2 would be 2.5. And if I take the square root of that, so 5 divided by 2, and I take the square root, I get around 1.58. So the last step, if I do the distance to the distance to B compared to the distance to A, well, we get 1.58 over 1. So the distance to star B would be 1.58 times greater than the distance to star A. I'm hoping that with these examples that we've gone through, with the document that I put for comparison style question examples, I'm hoping that students are finding that there's kind of a variation on a theme. Identify what quantity you're trying to compare, make up numbers for the first case if no numbers are given, and then see what changes from the original case to the new case. And final step, what is the new case divided by the original case? Now, when we actually apply this to different stars, we see an enormous range of luminosities. Many stars that are relatively nearby the sun in our local neighborhood of the Milky Way galaxy are fairly dim, intrinsically dim, have luminosities less than 1% of the sun's luminosity, sometimes less than 1/1000th the sun's luminosity. In fact, we're going to see later on that these low luminosity stars are actually some of the most common stars in the Milky Way galaxy. However, every once in a while, on the other end, we can have stars that are literally 1,000,000 times more luminous than our sun, giving off 1,000,000 times more light energy than our sun. And there are some stars that are even around, like, I think 5 million solar luminosities is the current record. So again, we get this enormous range of luminosity measurements. And when we look at images like this, sometimes in different telescope images, you'll see these kind of spikes showing up. In fact, in the images of the James Webb Space Telescope, if you've looked at those, sometimes you'll see them showing up in a six-sided star, in a six-pointed star figure. These spikes in an image, they're not actual giant spikes extending off the star, as fun as that would be. This is a lens flare effect and a diffraction effect with some of the structures that make up the telescope itself. Basically, when you see these spikes on the image, it's basically showing that that light source is too bright for the settings of the telescope. So those spikes on the telescope, those spikes on this telescope image are telling us more about the apparent brightness of this object. Okay. Even in pictures like this, where there's no obvious lens flare, the size of the images of these stars don't necessarily represent the sizes of the actual stars. Most telescopes do not have the angular resolution to actually resolve the size of the star. What you're seeing here is the brighter the star, the more some of that starlight kind of bleeds over into neighboring pixels on the camera that's actually taking this image. So when you look at an image like this, the larger the object, it doesn't necessarily mean that object is physically larger. It means that those images, those objects are brighter on the telescope, and some of that light is bleeding into some of the nearby pixels. So we've talked about how to measure the distance to at least nearby stars using this parallax measurement. And if we have both the apparent brightness of a star and we know its distance, we can actually use both of those together to identify what the luminosity of the star is. And in the next sessions, we'll talk about how to measure things like surface temperature, how to measure the mass of different stars, and the radius of different stars.